half of section 11.3 is higher order partial derivatives and Clairaut's theorem. So it's just like there are second and third derivatives that we can take for functions of a single variable, we can take multiple partial derivatives of a variable with respect to, well, a mix of variables really. This is two partials of f with respect to x, or two partial derivatives of f with respect to x. We've got partial of f with respect to x, and then the partial with respect to y. So the ordering is closest to the function is the first one taken, and furthest from the function is the last one taken. What we'll find is that for certain functions, the order won't matter, and that's exactly what Clairaut's theorem is. So each of these lines gives us some full notation for the situation, and we'll see any of this come up at any given time. Now, Clairaut's theorem states that if f of x, y is defined on a disk D containing the point AB, and the partial derivatives f of x, y and f of yx are both continuous on D, then f of x, y at AB is equal to f of yx at AB. So in other words, we can swap the order of these partial derivatives if those functions are continuous. Those second partial derivative functions are continuous at that point. Of course, this will extend to general functions of x and y, not just AB, if the function's continuous everywhere, if those second partials are continuous everywhere. So a reminder about the disk and fuller definition. A disk is essentially a circular region in the plane for which a function, like we're saying, might be defined on. So to describe that set in the plane, we have the following. So the disk D, we'll say at the point, centered at the point AB, is equal to the set of values x, y, such that, vertical bar such that, the distance from x to y to a to b, the distance from xy to ab is less than r for some real number r greater than 0. So that distance formula, remember, is x minus a squared plus y minus b squared, square root of all of that. So essentially, that will form a circle if you write out what this distance formula actually means, less than r. Less than r means all the points within that circle of radius r. So that defines the disk a little bit more clearly for us when we talk about these things. Some disks are open. In this case, this disk is open since it's strictly less than. Other disks will be closed. That'll be less than or equal to, including the boundary or not is closed or open, respectively. Now, find all second partial derivatives of f of xy equals sine of mx plus ny. So here's our function, two variables, x and y. And we're asked to confirm the result of Clairaut's theorem for this function. So in other words, find the two second partials and compare and make sure they're actually equal to each other if they're in fact continuous. So the first partial of f with respect to x is differentiate the outer function sine of x, or sine to get cosine. Differentiate the inner function mx plus ny, partial with respect to x, because it's a constant of m by the chain rule. The chain rule still applies for partial derivatives. Now, with f sub x, so the first partial of f with respect to x, we can differentiate once again with respect to x, and outer function is negative sine, and we get another factor of m to give m squared in total, and that's coming from differentiating the inner function. And we're just going to kind of repeat this over and over in each of these. And we see that f sub xy, similarly done, we get a factor of n instead of m. It's negative because cosine differentiates to be negative sine, and that n came out because the partial with respect to y now is n, this constant right here. So that's f sub xy, or the partial of f with respect to x and y. And to check the other way, partial with respect to y, again, we have sine differentiates to cosine, and then take the derivative of the inner function. Partial with respect to y is going to be n. Remember, mx is treated as a constant, so it's effectively 0. So we get that factor of n. Once we've got that, we can take the second partial with respect to y to get this function, and another copy of n. Cosine differentiates to negative sine, and then that n, of course, came from differentiating the inner function of ny. And if we go take f sub y, the partial of f with respect to y, and take the partial of that function with respect to x, we'll have what we have at the bottom. Again, the details are very similar to the rest. We end up with this function, which matches this function. And it in fact should by Clairaut's theorem, because sine of mx plus ny, both of those functions are continuous everywhere. So these partials should match, and in fact they do. It's a nice confirmation of Clairaut's theorem. It doesn't prove it, but it's confirming that that's in fact the case for this function. Now, mixed partials up to any order is possible. So in this case, they're asking us to find the third order partial of g with respect to r, and s. Okay, and the function g of rst is given below. E to the r sine of st is the function we're asked to differentiate. So our first derivative, first line, pretty easy to do. There's not a whole lot of work. First line, derivative of g with respect to r of rst, but we're just differentiating e to the r. Well, that's just e to the r, and it's times the constant sine of st, since we're taking this derivative with respect to r. So we just have e to the r times its constant sine of st. Now, continuing along, we need to find the second derivative of g with respect to r. And again, same thing, nothing much changes there. And our last step, derivative of g sub r with respect to s. This is the partial derivative with respect to s. This is a constant now. Our outer function is sine, so that differentiates to cosine, times the partial derivative of st with respect to s, which is just the constant t with respect to s by the chain rule. So this is the result, g sub r(s). We get e to the r cosine st times t. A better way to write this is below, but of course either are correct. So that can be done indefinitely. Ad infinitum, we could take more and more partial derivatives as needed. They're about as easy as normal derivatives are. One last thing to see is just confirming solutions of a differential equation. In this case, it's actually a partial differential equation. What we have here is Laplace's equation. Partial of u with respect, second partial of u with respect to x here, plus the second partial of u with respect to y is equal to 0. Any function u that satisfies this equation is a solution to this partial differential equation. So we're given two different functions to check. So the first function we're given is e to the x cosine y. That's the function u now. They want us to see whether or not this is a solution of Laplace's equation. So of course we need two things. We need to know the second partial of u with respect to x and the second partial of u with respect to y. So to carry that out, first partial is this. U with respect to x, we're just differentiating e to the x. So we get e to the x times the constant cosine y. Do that again, and it looks very similar. Derivative of e to the x is still e to the x times the constant cosine y, since we're taking the partial derivative with respect to x. On the other hand, when we do du with respect to y, partial u with respect to y, we differentiate the outer function, the cosine function, and that's how we end up with a negative sine of y, and then times the constant e to the x. Do that again, we end up with negative e to the x cosine y, differentiating sine of y to get cosine of y. The negative's still there, and we can confirm that this actually is a solution of Laplace's equation by starting from the beginning of the equation on the left. We add second partial of u with respect to x plus second partial of u with respect to y, and those in fact add to 0, and that's exactly what Laplace's equation states. So this is a solution to Laplace's equation. Now, another function, u equals x squared plus y squared. So take the first partial of u with respect to x, we get 2x. Second partial of u with respect to x is 2. Remember that this y squared is a constant when we take the derivative of u with respect to x. Similarly, for derivative of u with respect to y, or partial of u with respect to y, we get 2y. Again, the x squared is 0. That's a constant with respect to y for partial derivatives. And again, we get 2, taking the second partial of u with respect to y. Now, the result of this is, for Laplace's equation, add second partial of u with respect to x with second partial of u with respect to y. We get 2 plus 2 as we have above. And those, in fact, add to 4, which is not 0. So this is not a solution to Laplace's equation. So pretty easy to check. So if you're asked to check whether or not a function satisfies an equation or is a solution to it, you're just making sure it satisfies the identity. One of the key steps to learning differential equations is to understand what a solution actually does for a differential equation. So that's it for 11.3. Partial derivatives, higher order partial derivatives, mixed partial derivatives. We're going to see these a lot throughout the course, so be sure to practice this section. It is fun, but it's also a very important thing to learn for the rest of the class.